Y9 RC circuit. This is a resistor and capacitor. We have a battery. This is a thick line, thick and narrow line indicates the negative sign, and this is a positive sign. Here, point D is always 0, so this one is grounded. So Earth is here, so it is always a 0 volt, and this is a positive. So the current tends to flow from the positive terminal of the battery. Okay. By the way, at t equals 0, this capacitor was completely discharged because this terminal is a positive sign. Charge will be accumulated. Positive charge will be accumulated in here, and negative charge will be accumulated here. Our convention of writing Q for the charge of a capacitor is in such a way the current flows in to a plate to accumulate positive. Delta Q becomes positive. So from this convention, it is right. I flows in, Q increases. So remember, right now, the current flows counterclockwise. In this figure, until t is less than t0, this one is 0 volt. The origin is missing, but I hope you understand this is origin. So this is 0 volt. This is 0 and this is 0 because there is no charge at all. That is the initial condition. The circuit is grounded at point D. Yes, right. And the switch is closed. If there is no switch at all, it is impossible to have Q equals 0 forever. So in here, less than T0, the circuit must have been open. It was not closed. And somebody closed the switch at T equals T0. That's the situation. And right after turning on this circuit, current flows and the capacitor is being charged. The circuit equation here, if you write down this one is a VA, we have a VA. When we cross this capacitor, potential, this is positive, negative, potential decreases by how much? Because Q equals CV, V equals Q over C, and this is the difference between the two plates. Because the potential decreases, I have to subtract Q over C. And then current flows. When current flows, the potential difference between the two terminals of a resistor is delta V equals IR, and we know resistor consumes energy. Therefore, potential decreases if you follow the direction of a current. So when you pass through this resistor, you have to subtract IR. And when you return to here, this is the potential of D. and we were told that this is exactly 0. And from here, we can write Ri plus Q over C equals VA. And this graph says there is an amplitude in here, V0, that is a 1 volt, and there is a step function that is called theta function, t minus the t0. Theta function, the step function, is a 1 when the argument is a positive, and it vanishes when the argument is negative. Okay, so we are ready to solve this problem, but we know the current is the time derivative of charge. So why don't we replace this one with the Q dot, and why don't we divide both sides with R? Then we have Q dot, Q over RC, and V0 over R, and this is the equation of motion, this circuit equation. It is quite similar to the problem of what? Did you solve this problem for damping only? Wait, okay. And this is, we learned harmonic oscillator and damped harmonic oscillator and driven damped harmonic oscillator yesterday, I believe so, right? So using that method, we would like to find the general solution of this problem by finding the general solution of the problem with the right-hand side is exactly 0. That is called a homogeneous equation. And homogeneous equation is of the form Q over RC equals 0. This is actually integrable. How? This is a dq over dt plus equals minus Q RC. We multiply this one to right-hand side. So dq over Q equals minus RC dt. This is log Q equals after integration, log of Q, so 1 over RCT. So Q, the initial value subtraction, Q over Q0 equals exponential minus T over RC, something like that. So that's the reason why we have the solution. Here, in this case, I have integrated from 0 to t, but now we need to evaluate this one from t0. So that's the reason why I used the subtractive value t minus t0. And the coefficient is to be determined by using the initial condition. As we know, when we substitute t equals t0, exponential becomes 1. And because e to the 0 is 1. And we were told that the charge at t equals the t0 was vanishing. So as a result, on the left part, in this region, Q is absolutely 0. The C0 is 0 and Q is absolutely 0 before the event. However, homogeneous equation is exactly the same equation for t equals less than t0. However, if t is greater than t0, this one becomes 1, so we have a finite base. Actually, the particular solution of this problem is trivially obtained by substituting a constant. Then if I substitute the constant, this one disappears, and Q is just RC V0 over R cancels. So CV0 is the particular solution. Very simple equation. So we know what particular solution is. And then general solution is I make a carbon copy of a homogeneous equation solution. So plus C e to the minus T minus T0 RC is the solution for T is greater than T0. Again, by making use of the initial condition that charge Q is 0 at T equals T0, that means if I substitute T equals T0, this one becomes a constant, and let me call this as a calligraphic C, or as C2. So CV0 plus C2 equals 0. In such a manner, we can complete the calculation. So substituting the initial value, this one must vanish at T equals to T0. In that case, we can determine the C as like that. So this is the solution of charging process. Initially, there is no charge in the capacitor. Okay, by making use of this, we can do a lot of things. For example, potential at B, that can be obtained. I told you if I pass it, this is Q and this is minus Q. If I move in this way, because I know this VA, what VA is, if I pass this, I need to subtract Q over C, right? So we know the answer for Q of T, so we substitute this Q of T over C. And VA is given in the problem. This is the answer. Substitute. C cancels because we have divided C. And for T less than 0, it is a trivial. T greater than T0, it is 1. So V0, 1, K cancel. And this is the answer for the point B. And CD difference. C is here. Current is flowing this way. So C is always higher than D. You need to remember where the C is higher or D is higher. You need to determine, you must know. That's quite important. So C is higher, and then what you usually write, Ri Q over C, this kind of thing is assumed to be positive. So in this manner, you must not be confused with the sign, either plus or minus. Anyway, now you have determined the current. This can be determined by taking the derivative of this. However, we have determined the current in this case by making use of the potential difference between the two terminals of a resistor. Okay. So from this, we have determined, you can see current decays. Charge at the capacitor increases. So the charging process is very fast when you just plug in, but it takes longer time and actually infinite time to fill by 100%. If you want to charge your cell phone, they say it is completely filled by 100%, but actually it is impossible to fill exact 100%. That's a lie. Understood? And it always takes a longer and longer time to fill it. So this your handphone display is lying. It is not physical to fill by 100%. They are liars. Anyway, that's not really important. It takes time and then okay. Then next one, energy problem. We know what the charge plus Q minus Q, what the charge is at time t, and what the current is. I want to compute the electrostatic energy saved inside the parallel plate capacitor. Okay, this Q square over 2C we learned. Let's substitute. We can expand. That's it. We can compute the energy spent by the resistor I square R. We know the answer for the current. Substitute trivial integral, the current squared, the amplitude, and this one we have final result. Compare these two. Energy spent by resistor. As t goes to infinity, what's that? It approaches this one, disappears. T goes to infinity is 1/2 CV0 squared. Here, as t goes to infinity, what happens? This one disappears. This one is also CV0 squared. Okay. Sum of these two, electrostatic energy you save and you spend. So it is lost one and saved one. Sum of them, sum, this one cancels, and we have, what's that? This one cancels, right? And this one and one adds. So we have factor of 2 and 1 minus or something. Again, as t goes to infinity, this one disappears. So this is the total energy transmitted from the battery, right? But what you have in hand, the saved energy inside a capacitor, is just only 1/2 of it. So it is natural to lose your energy. Understood? That is independent of the size of resistor. The resistance independent. The lost energy is always equal to the saved energy. So you are losing your 1/2 of a total energy. That's the key point. You need to know how to evaluate the time constant of RC circuit, and this one determines how fast it grows up or decays, right? And there are various numbers useful to remember, at least 4 digits. Using this, you need to know the numerical value of what the time constant means. Capacitor charge by 60% and this 87%, something like that, is this tau and 2 tau represents this percentage in the numerical sense. Remember. Next, this is discharge. There is no battery because you have filled it with Q. So we have plus Q and we have minus Q. What happens? So the switch was open, and at t equals t0, it is suddenly closed. Then what happens next? In this case, the current flows out. Current flows out in opposite direction in comparison with the previous case. Current flows in to fill the charge. However, now charge is being lost. Understood? So by losing the charge, that is called the discharge, the potential will decrease. Anyway, once the circuit is closed, there is no battery. This equation is trivial, identical to what we have found in the previous problem for the homogeneous equation. Therefore, it is C is just nothing but Q0. That Q0 is the charge contained inside the capacitor at t equals T0. Using this Q, you can take the derivative to find the current. Oh, we have negative sign on the current. Why? We used to define the direction of current in this sense counterclockwise in the previous case, because when I flows in, Q increases. This process is a Q decreasing process, discharging process. But the definition of a current is always chosen as the when charging process is happening, our current direction is defined in such a manner so that the positively charged plate is being charged. That's the reason why we have negative sign on it. These are tricky, but you have to remember it is a very important physical sign. Left or right. Okay, after that, everything else is straightforward. So, detailed calculation for evaluating such kind of electrostatic energy saved inside the capacitor and the energy lost by the resistor. You just follow the calculation. What's that? It's the same problem is surviving. I didn't erase. You don't have to worry about this. And remaining piece, okay, that's the remnant of last year problem. Students have complained me a lot. Why we should solve this very difficult problem? So I give you all the details of the complete solution for these problems. And if you're interested, then just study. It's a little bit difficult application, but once you solve this problem, you completely understand what's going on inside the capacitor.